Smartness is not that relevant for being creative in math. It's more about your experience and your sensibility. These things are going to shape your vision of the world, and it's going to make you think about something that somebody else would never think about. It is important that everybody finds what he likes in life. I'm very lucky I'm doing a job that I enjoy. My work and my passion are the same thing, so I hope I can show how beautiful math is and how amazing being a mathematician is. I'm currently a professor at the University of Geneva. For me, math is really something that I share with people. When learning mathematics, we are told not to make mistakes, but that doesn't match my experience as a mathematician. I cannot tell you the number of wrong arguments I describe to my collaborators, but often they just bounce on it and realize that this is saying something else. They say, no, your thing is wrong, but look, if you modify it, then it's saying something interesting. Making mistakes is just an important component of the creative process, and you have to teach younger people how to accept that. Once they start to get it, math becomes more joyful. Statistical physics is about deriving global properties of a huge system by analyzing the interactions between its tiny constituents. When you try to do so, you realize that these systems are extremely complex. Think of a fountain. If there is wind, everybody knows that the water is pushed in its direction. But there is no way you can track the behavior of each drop of water. So, what do? Instead of trying to understand the behavior of each drop, you look at the probability of how the drops behave. And by forgetting this hopeless quest of understanding the entire system, you can do something simpler, which is to look at what is the typical behavior of this system. What is true for fountains is also true for other phenomena, and the one that is dear to me is the question of magnetism. Magnets are made of tiny constituents we call dipoles, and their interaction is extremely complex. So again, you use probability to construct a system, and this is called the Ising model. Now, there have been thousands of papers on this model, but most of them were not dealing with the dimension of real magnets. My co-authors and I developed a new probabilistic insight based on what is called percolation theory. Its aim is to understand the phenomenon of a liquid moving through something, like water over rocks. It turns out that these properties are linked to the dipoles in the Ising model. Imagine you put a bottle of water in your freezer. When it reaches 0 degrees, the volume changes and the bottle explodes. This is a discontinuous phase transition. For magnetization, things are different. Imagine you pick a magnet on your fridge and you heat it. The strength will decrease continuously until it reaches 0 at what we call the critical temperature. Your magnet won't stick to the fridge anymore. It's an example of a continuous phase transition. It's what you see in your everyday life, but it's very difficult to prove mathematically. But using percolation theory, we did finally answer this question in the three-dimensional Ising model. The most beautiful thing is that you can apply percolation to very general statistical physics systems. Of course, it comes at a cost, which is that the percolation models are more and more complicated. That's why it's very important to me to keep trying to discover new mechanisms in percolation in order to build the most general and robust theory possible. I'm also a permanent professor at the Institut des Hautes Études Scientifiques. I was raised in Bure-sur-Yvette, where the institute is, so it's a little bit like getting back home. The institute has been one of the most important places for the development of algebraic geometry. Being the first professor in probability means that I should also make this place an important place for probability itself. After I arrived at the institute, we put blackboards outside in the park. When you walk in nature, part of your body is just not really with you. It's in the place where you are. And the other part, which is the one doing math, is somehow doing it better. As a young mathematician, I was super enthusiastic, always doing research, sometimes not managing to find sleep. I was just too much into it. But then my wife Séverine and my daughter Anaëlle came and they showed me how to, sometimes step back and enjoy these other things that are outside of math. It changed me as a mathematician. I had less time, but it was better time. Séverine teaches philosophy and French in high school. We have been living in France next to Geneva for many years. My work is crucial. I love my work. I live for my work. But I also live for the rest of my life. And I never want that to change.